So anyway, so later on I just introduced the word cryptography. It is applied in two different ways. One is encryption, which is just for maintaining secrecy, right? Only the sender and the receiver should know the what is there inside. That's the secrecy. And the second one is authentication, saying that yes, I am the one who is sending you this. You just have to. The receiver should be knowing that, okay, he should be able to verify that yes, the person who is sending this is exactly that person, not by some other name. Okay, that's authentication. So there has to be what is called as a digital signature with that. Okay. So in order to perform all these, right, these kind of operations, you need to have two kinds of keys. One is called as a public key and one is called as a private key. So who is using what type of key will define whether you are doing encryption or authentication. Okay, right. Now I need to go a little bit detail about this. Maybe I can save some time by directly drawing a block diagram. Okay, so right. So let's see. The whole concept is called as public-private key authentication system, right? So if we are using that for, say, encryption, the first technique is encryption. If we are going to do encryption, our intention is to uh, maintain secrecy. So our idea here is that a person B is going to send a message to A. Okay, this is what I want to do. So B has some text which he or she wants to send, right? It will directly go into an encryption algorithm. Okay, this is the encryption algorithm. Now what happens here is, since this is the encryption, right, B is actually going to use a specific key that is called as the other person, that is whoever he or she is intended to send the message to, right, that person's, that is A's public key will be used. Okay, so this is how the message of B gets encrypted, right? Which means as soon as you get an encryption, as soon as you get the text into the coded format, it's encrypted, you get a cipher. Okay, it's a name, same name, and it reaches A now. So A will perform what is called as a, it's decryption. Okay, so whatever algorithm is used on the encryption side, if it is RSA, you will do the inverse of that, right? So there are several standard algorithms we have, right? Any one algorithm is fine. Okay, so there will be a decryption algorithm inside the system of A. So this side is actually B. Okay, this is B. It's just being sent. So decryption algorithm will get back the original text. Okay, this is happening on A, okay, on the system of A. But now what is important is the decryption algorithm is going to use another key, okay, but that's not the same key as the public key that is used by B. This will be A's private key. So that's why we have two keys, and two keys, both the keys are being used in this fashion. You see why A's private key is used, because, right, only A can read that. The intention is to send a message from B exactly only to A. Okay, right. So nobody else should read it, means A should use the private key to read that. Those who, if private key is not available, you cannot read it, right? So that's what is encryption. So now we see how this concept changes when I want to perform what is called as authentication. Okay, so my intention is to send message B, send a message from B to A, right? But want to make sure that B puts a signature over there saying that yes, I'm the one who is sending, right? So that's what is authentication process, right? Yeah. So once again, I'm going to have a text. This is from side B, right? So there is encoding that is happening. Now you see the name slightly changes. This is also encryption only. You use an encryption algorithm, but just to differentiate, we use the word encoding. Okay. The same algorithm which we used earlier for the previous process can be used here. No problem. It's actually the encryption only. But just to differentiate that the terminologies between the authentication and the encryption, we use slightly different words, that's all. Okay, again I need a key here. So the key which is used for authentication is not related to A. When B is using this, B will use his private key. So this is B's private. Okay, B is going to use his private key just to make sure that it's just to show that yes, I'm the one who is signing. Okay, yeah. Fine. Then you get a cipher. So cipher reaches to the A. So on other side, I have a decoding algorithm. Right. This gives you the text back. Okay. But now what is being used on the other side is the B's public key. Okay. So you see the difference, right? When, at what point and whose keys are being used. Okay, so that changes the whole concept, right? If B is sending and using A's public key on one side and A is using the A's private key on the decryption side, then this is encryption decryption. At the same time, authentication uses only B's keys related to the sender. Okay, so you see the difference. This is what is the basic idea of cryptography. All right. Yeah. Now, the one which we are going to study now is actually the hybrid. It's not just these two separately. It's actually the mixture of that, and we are going to call that the ECC is not any of these two types. It's actually the hybrid version. So this is called as a public key crypto system, which is a hybrid technique which uses both the techniques, right? It uses normally uh, both keys, right? Both private keys, both public keys, A as well as B. Okay, so right. So you see, we have I can write a message source. So it actually goes into encoding first, right? So why we use different terms, because we just have to understand that what exactly we are doing. So you see, this is encoding, means it is a part of authentication. First, the sender has to do an authentication initially before the process of encryption starts. Okay, followed by encryption. Then we have the message will be sent after this in the cipher format. So you have decryption happening on the other side. Okay, then we have decoding, right? At a later stage, I get the message back. Okay, so let me, these are the blocks of our system: decoding and a message. Okay, so normally this is the step-by-step procedure that takes place. But now definitely I have to include the keys, correct? So normally on one side, that is side of maybe A or B, right, you have a source which generates a pair of keys. We call it as key pair generator. This is, if we want to have public and private key for A will have a key pair generator. At the same time, B also wants to have it because we need to generate the public and private keys of B as well. Okay, so you have key pair generator on the other side as well. Okay, so now what happens? This key pair generator is used for the encoding and the decoding, correct? That's how I connect this one. So this key is generated. See, if I go back to the encoding process, you can see that encoding algorithm needs B's private key on one side, B's public key on another side. So that's the pair, correct? That's why it is connected in this fashion. Key pair generator sends the private key over here and the public key to the other side. Okay, at the same time, the other key pair generator also sends two keys, correct? But it is going to send the public key to this side because this is encryption, correct? Public key on this side and the private on the other side. So, right. So if I call this side as B, right? So we know that B's keys are being sent on this side and A is on the other side, means A's public key and A's private keys are used for encryption and decryption. Okay, so this is for A, this is say for B, and in this case also B is sending a message to this, right? So the basic idea is that the ECC which we are studying now is a specific type called public key crypto systems. Okay, it uses encoding, encryption, decryption and decoding. All the process will be included in this. So the idea is that if there are two users, source to destination, source will use a pair of public and private keys, destination also going to use a pair of source, private and public keys. Okay, now so this technique actually, I think we have this the same thing mentioned in the paper which you sent earlier, has some applications. All the applications are mentioned over there. Let's give the name. So where do you apply applications of the specific ECC? One is called as, this is a very famous algorithm. This is DIFFIE, Diffie-Hellman key exchange. We can use it over here. And another, the first one is related to encryption, decryption, and second one is authentication based. This is called as the digital signature algorithm. So widely used in these cases. Now, what is the central part of the whole algorithm, right? This whole crypto system uses two things, right? The first thing is you have to build what is called as uh, an elliptic group, right? Elliptic group needs to be formed, and second uh, base point here is that the point multiplication. Okay, so point multiplication basically refers to you repeatedly add the points. like P becomes 2P, then 3P, then 4P, like that. Okay, so we'll write that now. So that is central part of the crypto system is, first thing is you need to form, or I'll write forming elliptic group, and the second one is called as a point multiplication, right? So point multiplication basically refers to, we are going to perform repeated addition, okay, of any points, right? It can be something anyway, we'll solve problems later. So that is, you can have P, 2P, 3P, etc., or P plus Q, P plus 2Q, P plus 3Q, and so on. Like that also you can do, right? So we have repeated addition that is coming into picture. That's what is important. Okay. So now we look at what is called as the standard procedure. Now we'll restrict this to the ECC only, not general. So far it was general crypto system, right? But when it comes to the ECC crypto system, right, we see what standard procedure you are going to follow, right? So initially, there is a sender and there is a receiver, and they want to use this kind of cryptography, crypto system to be implemented for the communication. Okay, so first step is both, say, sender and receiver, both of them will agree to something like the standard data values, what we call, okay, to data values. For example, it could be, when it comes to the ECC, it could be the elliptic curve equation, okay. There is an agreement between them, in the sense you define what A value you are going to use, what B value you are going to use, okay, and we require a prime number, correct? So what is the prime number? Prime number P. So what prime number P you are going to use, okay? Initially you both have to agree, yes, right? So only the sender and receiver should be aware of this, okay. Unless and until both know, they cannot generate their individual, what you call, the private and public keys, correct? So they are basically developed and generated internally from these numbers, okay. Okay, now all the points that lie on this curve forms an elliptic group. Okay, so using these agreed values, uh, both senders and receivers should be generating what is called as an elliptic group. Okay, which is nothing but, you should know all the points that lie, okay, on this curve, right? So that's the step number 2. This is elliptic group. Okay, elliptic group is uh, computed from the equation of elliptic curve, right? Then the next step is nothing but, there is what is called as a base point, right? This is a base. I'll show the use of base point when we go to the algorithm itself, okay. But there is a necessity of a base point, right, that should be selected right? It is something like a generator polynomial equation or something like that. You generate something based on a base point in every operation, every mathematical operation that we use. Okay, so that's what is called as a base point, and this point will be selected from the elliptic group itself. Okay, so a base point, I'll write capital B. Okay, small b was used earlier. This is the small b, indicating that this is a part of elliptic curve. Okay, a base point B should be selected from the elliptic group, right? I'll write it as we can understand this process as a generator operation. Yeah, correct. So what you do, you have a private key. Into this base point, you get a public key. Correct. So that's why this is used. All right. So this B is the base point, which is helpful in generating the public key later. Okay. Fine. So this will be a number, right? Normally, anyway, all the points on the curve are all the points are actually the whole number. That's what discretely located points we know, right? And generate the private, but a private key into a public key later. Okay, now after this, once this is done, each user generates the keys. Okay, so each user generates uh, the private and public keys. For example, uh, for private key, you take an integer value, right? That is between 1 and p minus 1. Okay, so this is integer, say x, we are selecting it between which you had earlier selected. That number you can, okay, any number. Then is a product of okay, we have to use a private key, product of private key and the base point. Okay, so we call this as maybe q is equal to x is a other key, that is a private key, multiply with b. So you see that if x is a coordinate, right, bx is nothing but it's like you had p as a point and multiplying that by a number, right? So 4p, 8p, 6p, like that. So this is b into x. X will be your point, 1 point. Multiplying that by, say, b is 200, means 200p is what you are calculating. So overall, mathematically, we can write. So we originally had, when the process begins, you know that you are going to use y square is equal to x cube plus ax plus b with known values of a and b, but this is a mod p operation always, and you select the points x comma y, right, such that they belong to a prime field zb cross zp. X can take any values in zp, y can also take any value in the zp, and also you define what is called as a B, and you call it as a base point for this whole process. And from this, right, out of this you always get a private key, right, that is directly between 1 and p minus 1, including both of them. Then get a public key, that is q is equal to x into b. Simple operation. This is what we are supposed to do. Now, in the sense, the set of prime numbers which are there in your list, out of all prime numbers, within that, all the integers, z is integer, sorry, integers of integers present within that, what you call the prime number you selected. Okay, z is in, huh. To be the integer values, right, less than that given number. Anything, yes, because this is anything, because you want to, what you want to send is, right, is completely depends on what message you want to send, right? That's why we are writing in this fashion. The x comma y will, yes, any point can be. Okay, now for let's consider a specific scenario that the a say a wants to send a message, encrypted message to b. Okay, send b. This is what we want. Now what happens, both agree on the base point, right? So first you select a base point, b is selected. So once that is done, you have to create a public key and the private key. So for a, let us say there is a private key, right? Say this is some a. Okay, then we have a public key. Let me denote this as PA. So this is simply A into capital B. Okay. So similarly, same thing will happen with B, right? B will generate a private key. Call this is P associated with this. So this is B is the B into capital B. A will collect a text, right? So something, some message, right? So A takes on message, that is say some message, I'll call it as M. Okay, and performs the encoding to Pn, right, which is actually present on the elliptic group. Pm on elliptic group of points, so that one single character which you want to encode becomes a two-dimensional it's like x comma y. So one message, like the message could be say the letter L, right? But for that letter L, I get two coordinates after the encryption, right? I get 255 comma 835 maybe. Okay, so we'll see that process now. Okay, how that happens and how to, we'll solve the problems as well. Okay, so this is the overall procedure, right? Now the algorithm that is used is as follows. Okay, First, we'll look at an algorithm, then we'll try to solve a problem based on that first. Okay, so definitely you have to start with this. Y square is equal to x cube plus ax plus b, indicating that a and b are predefined. You will agree to a specific value. So what happens here, right? Since we are dealing with number, the letters a, b, c, d, e, f, etc., whatever we have, right? So that needs to be represented as a number. Correct? So then look at the concept of sending the text. So what is a plain text? It means the plain text includes numbers. Each number is represented in the same way. It's not going to be changed. You can have 0 to 9. So in my message, in my original text, if there is a number 0, it will be represented as 0 only, but later on it will be converted into two coordinates. Okay, so 0 to 9 will be kept as it is, as a plain text. Okay, initially, right? But later on, definitely this has to be converted into a different elliptic uh, points on the elliptic group. Okay, that's one thing. Then my plain text also includes, right, the English characters. Right, but I want them to be converted into numbers only, right? So what you do, 0 to 9 is already occupied. So you start from 10. 10 is A, 11 is B, and so on. Okay, this is 10 to last number will be 35. That is Z. So initially, you can do something like, see, this is just to understand the whole process, right? There can be something like there is no differentiation between capital and small letters for the time being, right? Capital A as well as small a could be 10 only, okay? Similarly, capital B and small b is 11 and capital Z and small z is 35. But later on, if you want to encode, right, capital and small separately, right, you can continue from this. The 36 will be, right, if you consider 10 to 35 as capital letters, 36 onwards you can assign for small letters. Okay, so that actually adds up more complexity to your encryption. That's all. Okay, fine. But just to understand the whole process, we'll restrict to 10 to 35 and 0 to 9. So totally 0 to 35. So if you have any text like ABC 123, right? My plain text corresponding to this will be A is nothing but 10, B is 11, right? So C is 12. Then I have 1, 2, 3 as it is. So it's still 1, 2, 3. Okay, A, B, this 1, 2, 3. This implies it is actually my plain text which I want to send. This will be converted into a cipher, then it will be sent. So, so this is the overall idea now. Okay, this format first before I start the process. Okay, that is the, let's denote that as such that you convert the given text into its x value directly we can calculate. Okay, so in the sense we will be having the values of p already defined. Okay, what prime value you are going to use will be defined earlier. Anyway, we know that, that's why I have not written here. Okay, so what I do here is you use a public variable here, and okay, I'll write one more thing just before this. So each of the character is a number, correct? So that is what I call it as m. So convert plain text into what you call the numbers, the series of numbers. For example, I'll write, right, say b is encoded as m which is equal to 11. This m is what I'm going to use in the next step, so don't get confused what is m. That's why I think I missed this point previously. So for example, b is, so this b, what you see here, this is the B that is encoded as 11, right? So this is my M now. M has some value. Which I understand is M, right? Its value is 11. So now I choose K such that I get my X value. So calculate. Yeah, it should be more than. It cannot be small value like this because, right, that gives us a lot of restriction. I don't get many points on my curve. Correct. I should have sufficiently large number of points on the curve, right? Because normally we take this around maybe 550 something or something larger than that. You take the values like that. Okay, that will be the p value. Okay, so I calculate the x coordinate of, right, x coordinate corresponding to this letter b. So this b can be converted into a possible x value which I calculate now. This is equal to the m, which is the message, that is 11, into the k value which you have chosen. This can be anything, right? There is no restriction on k. Okay, k can be even number, odd number, anything. No, not necessarily prime. Okay, plus I write a I value. Okay, this I actually varies. I varies from 1. I start from 1 to k minus 1. Right? Why it is? Because see, the operation which I'm carrying here is a mod operator and I am expecting integer as an answer, right? X is fine, you definitely x will become an integer by anyways. You choose m is 11, say k is 30, so 30 into 11 plus I is equal to 1 2 3 4 up to 29 if k is 30. Okay, this is definitely an integer, but y is not necessarily be an integer, correct? For this particular value of every time, that's why I am changing I from 0 to that number, because for every value of I you put here, your y will be different, correct? So calculate the y that satisfying the equation, that is y square is equal to x cube plus ax plus b mod p. Okay, find the value of y in such a way that you get an integer value under mod p operation. Right, this is very difficult. You don't get every point that you put over there, every I value you put over there will give you this. It's not true. Okay, you will change i's in such a way that I1 I check y is an integer or not, I'll check. If it is yes, you stop. Okay, you don't have to go further. If when I is 1 I don't get a y value integer, then I need to go for next process, make I equal to 2, right? Get a value y. If it is integer, yes, otherwise no, proceed further. I equal to 3, I equal to 4, dot dot dot, you go till I is equal to 1 till k minus 1. Out of this, one of them will definitely be this, because you are actually adding the I to the m into k, right? So x is automatically taking care of all the possibilities. So for a given x, sorry, please. Yeah, so I takes all the values from 1 to k minus 1, right? Which actually takes care of all the possible values of x that can come on the curve, right? And corresponding y, which is an integer, we need to select out of that. Okay, so calculate the y satisfying this particular equation, right? Right, I am expecting this to be an integer. See, it's m is what? M is your message, right? The integer which you have taken, right? So I am adding I, when this becomes once again k, this becomes m plus 1 into k. The m plus 1 is your next number, correct? So m, no, it's random, it's random. it is random, right? Since you want to bring the randomness into picture, you are choosing public variable as some k. Okay, all the k values, like if say k is 30, so 1 to 29 possibilities you have. That's all. You want to have more possibilities, make k bigger. That's all. Okay, when you increase k to a higher number, possible. That's also possible. You change the k in that case. Normally, in general, what we have seen is that any k will work. There is no scenario wherein you don't get an answer. Okay, one of the values from 1 to k will work. So again, it is suggested that there is no restriction on that, but it is suggested to take a bigger k value, not a very small, not like 5, 6, 10, not suggested, right? It's because of the same reason. If you take a smaller value, then maybe there is a chance, because I'm only expecting an integer value of y, right? So because of that reason, it is always suggested that you take a bigger value of k. Okay, now you see that you had a x, right? A specific x is calculated, right? And using that x, I got a y. If anyway, x is always an integer, and if by chance y also became an integer, then right, this implies m, the message m is coded as x comma y. All right, so you see, this is what I told. When you have a single number corresponding to the letter which is present in your text, that is converted into two digits, sorry, a pair of numbers, x comma y. Okay, now this x comma y is a part of your ciphertext. For each letter that is present in the original text message, you need to repeat this whole process so that you get a complete ciphertext. Okay, so yeah, please take your time. No issues. Absolutely fine. Yeah. An integer. So x plus b can be calculated depending on what a and b you have chosen initially. So answer, right, should be using that, I should be able to get a y. But the condition is that it should be integer. Okay, that answer x cube plus ax plus b is not necessarily giving you an integer value of y, right? Because of two things. One is there is a mod operator. Second thing, there is a y square. Correct. So because of these two reasons, you might not get a proper integer value always. So that value of x which satisfies this, there should be a specific rule defining what x value you are going to use, right? So that for that reason, the ECC uses mk plus I format. Okay, m is your message, k is a randomly chosen number which is fixed for the whole process, right? Plus a I value which varies from 1 to 1 less than k. So since you initially predefine this, I know what values of x are possible. Okay, for each value of x, you calculate the possible y. The first value of y which gives you an integer value will be considered as your answer. There may be multiple answers as well, right? So for say x value equal to 2, 8 and 10, y becomes integer, but out of which only the first value, the 2 for which you get a y as an integer value will be considered. Okay, you get an integer value. So that x comma y is considered as the code of m using the ECC technique. So how do you decode now? So this is an encoding process, right? The decoding is decoding can be done, right, by using, again, there are multiple levels of what you call encoding that can take place, right? Assuming that there is only one level in this case. Okay, so you apply the floor of, you have a x coordinate which is there in this, x minus 1 divided by k. So k should be known. If you don't know, you cannot. Okay, this is the one of the simplest technique using which you can go back from x to m, right? Floor means the lower number. Okay,